In this video, we will cover the following topics: using the VisSim transfer function block and its filter design option to design, discretize, and implement a second-order low-pass filter in floating and fixed-point format. The discrete update time and fixed-point format settings are adjusted to produce an acceptable fixed-point filter response. The VisSim matrix language, abbreviated VML, is introduced and used to perform precision calculations. Code is generated for both filters and executed on the Texas Instrument 28069M Launchpad. Real-time performance and CPU utilization for both filters are compared. In this section, we will apply the VisSim transfer function block and its features to design and simulate a discrete filter in fixed point and floating point. A second-order Butterworth low-pass filter with a 2 radian per second bandwidth will be designed using the VisSim filter design option. Then the filter will be converted to discrete, both in floating point and fixed point, and simulated. First, we'll create the continuous low-pass filter. From the Blocks Linear System menu, we'll place a transfer function block on the screen. Right-click on the block and under Transfer Function Properties, select IIR Filter. For Method, select Butterworth. For Type, select Low Pass. For Order, select 2. And for Cutoff Frequency, select 2. Click Calculate Filter, and Done. This is our continuous low-pass filter. The filter coefficients are displayed in the gain, numerator, and denominator polynomial fields. We'll save this filter as we will want to use it as the basis of comparison. Now we'll create a discrete floating point filter by copying the continuous filter block, right-clicking to view its properties. First, click on Convert Z to S. Since we'll be using a 0.1 millisecond sample time for the discrete filter, we'll set the discrete sample time equal to 0.1 milliseconds. The discrete floating point filter coefficients are displayed in the gain, numerator, and denominator polynomial fields. Click OK to complete the design of the discrete floating point filter. Now we'll create a fixed point discrete filter using the floating point discrete filter we just created. First, we'll copy the floating point discrete filter transfer function block, right-click to view the parameters. In the upper right section, click Fixed Point and select 8.32 format, and click OK to complete the design of the discrete fixed point filter. Now we'll simulate the unit step response of the filters to compare their performance with the continuous filter. Since they are 2 radian per second filters, the time constant is half a second, the settling time is approximately 2 seconds, so a 5-second end time should be adequate. Under System Properties, select End equals 5. We'll select a time step equal 0.0001 and click OK. Next, we'll need a unit step block from the Block Signal Producers menu. Place it on the screen and wire it to all 3 filters. Then we'll need a plot block from the Block Signal Consumers menu. We'll wire the continuous filter output to the red pin, the floating point filter output to the blue pin, and the fixed point filter output to the green pin. Now we're ready to simulate the filters. Click Go to begin. The floating point filter response seems correct, but the fixed point filter is outputting 0. Let's investigate why. Right-click on the fixed point filter to view its parameters. Observe the gain value is set to 9.99 e to the minus 9. This is a pretty small number. Does the 8.32 format we specified have adequate precision to represent this gain? 8.32 has 24 bits to the right of the radix point, so the precision is 2 raised to the minus 24. Launching the VML calculator window, located under Tools, VML Workspace, we calculate 2 raised to the minus 24 as 5.9 e to the minus 8. Well, this is not enough precision, so the 9.99 e to the minus 9 gain in our fixed point filter, which uses 8.32 format, is out of range at the low end and is rounded to 0, causing the filter to produce a 0 output as observed. One way to increase the precision is to modify the fixed point format. Let's experiment to see if we can find a format that works. If we assume the input will always be between 0 and 1, we can try the format 2.32. This produces a precision of 2 raised to the minus 30, which is equal to 9.3 e to the minus 10. Now the gain is in range, and it will not be rounded to 0. However, this precision may still be a little coarse and affect the transient and steady-state behavior of the filter. Let's try the 2.32 format in our fixed point filter and resimulate. Well, this looks better, but there's still significant transient and steady-state error between the discrete fixed point and the other two. Why is this? The transformation used to convert continuous transfer functions to discrete transfer functions contains the discrete sample time in its gain. Another way of increasing the precision of a discrete filter is to increase the discrete sample time. We've been using 0.0001 seconds for the discrete filters. Let's increase this to 0.001 for both discrete filters and resimulate. First, we'll construct the discrete floating point filter. We'll copy the original continuous filter, right-click to view the parameters, click Convert Z to S, set the discrete sample time equal to 0.001, and click OK. Now we'll create the fixed point discrete filter. First, we'll copy the floating point discrete filter transfer function block, right-click to view the parameters. In the upper right section, click Fixed Point and select 8.32 format, and click OK to complete the design of the discrete fixed point filter. Now we'll simulate the unit step response of the filters to see how they behave. Attach the unit step input signal to all 3 filters. We'll wire the floating point filter output to the blue pin and the fixed point filter to the green pin, and click Go. Well, the transient response looks okay, but the steady-state error from the fixed point discrete filter is significant. Let's see if we can reduce this by increasing the precision with the format 2.32 instead of 8.32. Click and Go to continue. Now the discrete fixed point filter response, both transient and steady state, agrees well with both the discrete floating point filter and the continuous filter. As we proceed, we will use a 1 millisecond discrete sample time and a 2.32 format for our discrete fixed point filter. Now we're ready to compare the percent CPU utilization of the discrete floating point filter and the discrete fixed point filter, both running on the Texas Instrument F28069M launchpad. To do this, we'll create a source model that will allow us to switch one filter on and the other off interactively. The input to both filters will be noise from analog-digital converter channel 0. We'll begin with the model we just developed and delete everything but the last 2 discrete filters. From the Embedded Piccolo menu, we'll select and place a digital analog input for F280X block. Right-click to view the parameters, set the channel equal to 0 and the type equal to analog, click OK. Connect the analog input to the discrete floating point filter. Copy the analog input and connect the copy to the discrete fixed point filter. Lasso the analog input and the discrete floating point filter transfer function and create a compound block named floating point filter. Similarly, lasso the analog input and the discrete fixed point filter transfer function and create a compound block named fixed point filter. Right-click on the floating point filter to view the properties. Check Enabled Execution, click OK. Control right-click on the fixed point filter. Again, check Enabled Execution and click OK. From the Blocks Boolean menu, add a NOT block and wire it to the fixed point filter. Lasso both filters and the NOT block and create a compound block named Discrete Filters. Edit the compound block to have 1 input and 2 outputs. Label the top output floating point. Label the bottom output fixed point. Label the digital input on equals float, off equals fixed. Right-click the compound block, wire the input pin to the floating point filter and the NOT block, wire the floating point filter output to the top output, and wire the fixed point filter output to the bottom output. Navigate to the top level of the model. From the Embedded Piccolo menu, select an F28 config block. Right-click to view the parameters, confirm the CPU, clock source, and JTAG connection values are set correctly, and click OK. From the Block Signal Producer menu, select a button block and wire it to the Discrete Filters compound block. From the Block Signal Consumer menu, select a plot block and wire the Discrete Filters compound block output pin 1 to the red input of the plot block and pin 2 to the blue input of the plot block. Before proceeding, let's save our source model as discretefiltercomparison.vsm. Now we're ready to generate code for the Launchpad target. Lasso the Discrete Filters compound block and select Tools Code Gen. Check the Include VisSim Communication Interface option, click Compile, acknowledge the DOS prompt, click Quit, and we have successfully generated code. Now we'll create the debug model by saving the source model as discretefiltercomparison-d.vsm. From the Embedded Piccolo Target Interface menu, select a target interface block and place it on the screen. Right-click to view the parameters. Check that the target execution file is using the .out file we just created. Confirm the sample rate is set to 1000 Hz. And check the Show CPU Utilization checkbox, then click OK. Unwire the Discrete Filters compound block and wire the target interface block in its place. Add a second plot block and wire it to the %CPU utilization. Under System Properties, set time step equal to 0.001, end equals 10, check Run in Real Time, Auto Restart, and Retain State. Click File, Save, and we're ready to test our discrete filters on the Launchpad. Let's plug our Launchpad in. After a brief initialization period, the Launchpad is ready. Click Go to begin running the simulation. After the out file is loaded, the simulation starts. Clicking the button cycles either filter. Blue is the fixed point filter, red is the floating point. Both filters are producing a similar response to the ADC input. The floating point filter CPU utilization is approximately 1.68%. The fixed point CPU utilization is approximately 0.19%. So it's well worth it to use the fixed point implementation. For this example, we are seeing almost a factor of 10 times less CPU utilization.